Hi, and welcome to part 2 of grade 11 Euclidean geometry. In charge of the lesson is Benedict Salakwana, popularly known as Prof. In this video, I'm going to introduce you guys to theorems that are covered in grade 11. And yeah, that's what I'm going to concentrate on. And I'd like to say this, guys, to you. Make sure, guys, you understand your theorems if you really want to understand Euclidean geometry. Remember, I told you last time that mathematics can only be well understood if the principles are understood. So please follow the thingy, the advice I'm giving you. Go and study your theorems, go and study your theorem. With every theorem that I'm going to introduce to you, make sure you take your time to fully understand it. So I'm going to make try my level best here to make you guys understand the theorem that I'm going to be giving you. So let us start with our lesson. Before I start with my lesson, there are things that I would like, actually, before I introduce you guys to theorems, there are things that I would like to discuss with you, which is what we call a conditional statement, theorem, and converse of a theorem. So those are the things that I would like to discuss with you. So first of all, I'm going to start off with a conditional statement. It plays a very important role in Euclidean geometry, even though one may say it's not part of Euclid. But I can also argue to say it's part of Euclid because theorems are also conditional statements. So I'm going to introduce you guys to conditional statement, and yeah, with that, trust me, I can guarantee you guys that your Euclid will be better going forward. You will master it. So conditional statement. Let me start with conditional statement. Conditional statement, also known as if-then statement. Conditional statement, also known as if-then statement. Statement is a statement in the form P then Q, where P is the condition and Q is the conclusion. Where P is the condition and Q is the conclusion of a conditional statement. So this is what a conditional statement actually is. It's a statement in the form P then Q, where Q is the condition and where P is a condition and Q is a conclusion. So that's what a conditional statement actually is. So in order for you guys to fully understand actually the conditional statement, you need to understand what is a condition and what is a conclusion. A condition, by definition, condition is something that must exist or happen. It's something that must exist or happen before something else can happen. Condition, by definition, is something that must exist or happen before something else can happen. And then we also have a conclusion. A conclusion is the result. Conclusion is the result of a condition. Result of a condition. Is the result of a condition. So before I go any further, I would like to give you certain examples. You guys are already familiar with what a conditional statement actually is. You know, in life, there are things that we do hoping that something will happen as a result. Things that we do in life hoping that something will happen as a result are conditional. We study hard hoping that we will pass a test. You know, as a learner, you study very hard hoping that you'll pass a test. That is a conditional statement. If you study hard, you will pass a test. So that is a conditional statement. So many things that happen in our life that are conditional. You exercise hoping that you lose weight. So those are also what conditional statements. You take medication hoping that you will feel better as a result. So that is also what a conditional statement. So conditional statement actually, it consists of a condition and a conclusion. It consists of a condition and a conclusion. It tells you that if one thing happens, then another thing must happen as a result. Another thing must happen as a result. So now let us get deeper into this. So one thing you need to understand is, like I said, there are things in life we do hoping that something else will happen. A condition, like I said, is the result, conclusion is a result of a condition. The only time a conclusion, we can have a conclusion is if there is a condition. There is a condition. So in order for you to have a conclusion, there must be what? A condition. Remember, I said a condition is something that must exist or happen before something else can happen, with conclusion being the result of that thing which has happened. I'm going to give you a certain number of examples in order for me to emphasize, to make it very clear for you to understand what is a conditional statement. And guys, trust me, if you understand conditional statement, it will be easy for you to understand your theorems. And if you understand your theorems, it will be easy for you guys to understand your Euclidean geometry. That is how it works actually. That's how it works. So I'm going to give you an example. Remember, I said with conditional statement, it consists of what? It is also known as if-then statement. So it consists of what? It consists of if and then, where if, the if part will always represent the condition and the then part will represent a conclusion. Remember, I said the statement is in the form P, then Q, where P represent a condition and Q represent what? A conclusion. So it means the statement must always consist of a condition and a conclusion, where the condition is represented by P and the if part here represent the condition, and the then part will represent what? Your conclusion. So I'm going to give an example. For instance, if I give you something like this: if it rains, then the ground gets wet. So this is a very good example of what a conditional statement is. So you can see this statement consists of what? Of the condition and a conclusion. And remember, I told you we can only have a conclusion if and only if there is a condition. A condition must be met first. If the condition is met, we know it must always be followed by what? By a conclusion. So for every condition, there must be a conclusion. So this one tells us that if it rains, then the ground gets wet. What does that mean? It means in order for the ground, based on this statement, in order for the ground to get wet, something must happen first. And what is that thing that must happen first? It must rain first. So if it rains, then the ground will get wet. So you can agree with me, the ground getting wet becomes the result of what? Of rain. Becomes the result of rain. Something must happen first in order for something else to happen. Something must happen in order for you to have what? To have a conclusion. So that which happens first becomes what? The condition, and that which will happen as a result of what happened previously will become what? Will become a conclusion. In this case, what's going to happen? It's gonna rain, and if it rains, then the ground will get wet. So the ground getting wet becomes the result of what? Of rain. Again, I told you about what? We spoke about if you study hard. If you study hard, then you will pass a test. Let us look at the conclusion here. The conclusion is you will pass a test. Guys, remember I told you I can only have a conclusion provided there is a condition. There is something that happened previously which led us into that conclusion. So in this case, remember I said conclusion will always be the result of a conclusion. So this is the result of what happened previously. What happened previously in order for us to have this conclusion? You studied hard. So if you study hard, we know under normal circumstances, if you study hard, you will pass a test. So in this case, you passing a test becomes the result of what? Of your condition, and the condition was you studied hard. So something had to happen in order for us to have this conclusion. So what happened? You studied hard. So after studying hard, then what was the conclusion? What was the result of studying hard? You passed a test. So conditional statement tells us that if one thing happened, then another thing must happen following that, but as a result of the condition, as a result. So you study hard, then you will pass a test. We can also talk about what if you want to lose weight. Guys, there are so many ways in which a person can lose weight. There are so many things we can do. One can tell you, there are so many recommended things. You know, people tell you there are medications and there are pills you can use, and one can tell you to work on your diet. One can tell you that you must exercise. So in this case, I will use what? Exercise as our condition. If you exercise, then you will you will lose weight. You will lose weight. So let us look at this. In this case, what is our condition and what is our conclusion? Our condition is exercise, and then the conclusion is what? Is losing weight. So you're gonna agree with me. Remember again, I told you we can only reach a conclusion provided there is something, there is a condition was met, something happened which led us into reaching that particular conclusion. So the conclusion, the result in this case becomes what? You will lose weight. But based on this conditional statement, it tells us that you will lose weight provided that something happened previously, and what happened was what? You exercised. So you exercising, if you exercise, then you will lose weight. So it means in order for you to lose weight, first you must exercise. That which you do first, which lead you into reaching a particular conclusion, will be called what? Will be called a condition. In this case, is the condition met? Yes. What was the condition? You exercise. You exercising. Exercising in this case means what? Your condition. The result of exercising in this case becomes what? You will lose weight. So remember, we can say so many things. One can say if you exercise, you will be healthy. Those kind of things. Yes, that is also correct. If you exercise, you will be healthy. You being healthy becomes the result. It becomes the conclusion of you exercising. So exercising becomes what? A condition. And then you getting healthier becomes what? Becomes what do you call this? A conclusion. So this is what the lesson actually is all about. I want you to understand the condition and a conclusion. I want you to understand that with every condition there is a conclusion. With every condition there is a conclusion. And I want you to understand again that there is no way that a conclusion can exist if a condition was not met. So a condition must be met first in order for us to have what? To have a conclusion. So that's what I want you guys to understand. But it's fine. I think I'm just hoping that you understand what is happening here or what I'm talking about. So that is what a conditional statement is all about. Something must happen. Something must happen first so that in order for something else to happen, and that which happened after becomes what? A conclusion. What you do previously or first becomes what? Becomes a condition. So let us now go to our theorem. So I'm going to define my theorem. A theorem, when you go to different schools, some they define it as a mathematical statement that has been proven or can be proven to be true. And trust me, there's nothing wrong there. There's nothing wrong. That is 100% correct. 100% correct. So, but with me, I like to define my theorems this way. So a theorem is a mathematical. I define a theorem as a mathematical conditional statement that has been proven or can be proven to be true. So that is how I define a theorem. I define a theorem as a mathematical conditional statement. Instead of saying mathematical statement, I say mathematical conditional statement. Why do I define my theorems like that? I've identified that all the theorems actually are conditional statements. They consist of if and then. Actually, they consist of a condition and a conclusion. They consist of a condition and a conclusion. Hence, I define my statement as conditional statement. Listen, I'm not saying how your teachers define the theorems, they are wrong. There is nothing wrong, 100% correct. I prefer to define them this way because it works for me. But now, with a theorem, it's a conditional statement. Okay, yes, before I go any further, if I say a theorem is a mathematical conditional statement, it means theorems must also be in the form if P, then Q. Remember we said a conditional statement is a statement in the form P, then Q, where P represents what? A condition and Q represents a conclusion. But with this one, with mathematical conditional statement, it is different because here, before we can accept that mathematical conditional statement, it must be proven. It must be proven. We don't just take it and say, yes, this is the condition. It must be proven. So in this case, with what I've been discussing, it was obvious for you guys to know. You know, if you study hard, then the result is you will pass a test. That one we don't need to prove it. It's something that happens every day in our lives. We've seen that happening. But with a theorem, it must be proven first. We don't just take it and say, yes, now we can use it. No. The validity of that theorem must be proven. Is it true that and will give us that? When I see this will happen. But we know a theorem must be in this form. It must be in the form if then Q. So it means it would consist of what? Condition and a conclusion. But remember, I told you that in order for a conclusion to be reached, there must be a condition. But with a theorem, before we accept the theorem, we need to prove the validity of what? Of the conclusion. Is the conclusion really the result of that theorem? Does it satisfy that condition, I mean to say? Remember, I said this is the result of this. Sometimes the conclusion may not be true for a particular condition. It's like if I say to you, if you study hard, then you will fail a test. So do you think that conclusion, do you think that is a true statement? It is not a true statement. It is not a true statement. So the moment a statement, we say the statement is not true if and only if its conclusion does not support the condition. Some conditions may not support the conclusion. So some conclusions may not support the condition. So that's how it works. That's how it works. But with a theorem, the good thing about theorems, the moment I come and state you a theorem, it means that theorem has been proven. It can be used now. It's there. It has been proven to be true. So it means it's been accepted now. It can be used, it can be applied. It can be applied. So now, for instance, let me give you an example here. If I say to you, if A equal to B and B equal to C, then A is equal to C. Let us look at this as a theorem. Is this statement consisting of a condition and a conclusion? Yes. Remember we said the if part represents what? The condition, and the then part represents what? The conclusion. The question is, remember the validity of a theorem is its conclusion. The conclusion must support the condition. So the only way you can be sure is by proving your theorem. But with us we give it because we already know. But we also teach you how to prove those theorems. We give you a theorem, we prove it. We give you a theorem, we prove it, so that you can see that the theorem is valid. Now let us look at this. Why am I saying this will be the result of this? Why am I saying A will be equal to C? Because from what was given to us, it was given that A is equal to B and B is equal to C. How did I come up with A being equal to C? Is this the result of what we are given? Yes. Why am I saying A is equal to C? Because if you can go back to the condition, it is given that A is equal to B and then C is equal to B. Mathematically, remember we say things that are equal to the same thing are also equal to one another. If you say A is equal to B, you say C is also equal to B. In other words, we are saying as a result, A will be equal to C. Why are we saying A and C are equal? Because both A and C are equal to what? To B. So in this case, this will be accepted because now I have proven it to be what? To be true. It can be used as a theorem. But if I come and change, let me change my what do you call it? My conclusion and say A will be equal to D. Where is this conclusion coming from? Is this supporting what is given to us? Will this be the result of the condition given to us? Where am I getting the statement A equal to D? Because what I'm given here is that A is equal to B, B is equal to C. So from this, the only thing that I can be able to come up with as a conclusion is that A and C will be equal to each other. So it means in this case, the statement is not what? True. So the reason we prove theorems is because we are trying to avoid this kind of things where a conclusion won't support the condition, where the conclusion won't be the result of that condition. Remember, with every condition, you must be able to conclude. But the question is that conclusion correct? But in this case, yes, this will be what? This will be correct. It's a conditional statement, which is a true statement, this one. It's very true. A is equal to B, B equal to C, then A must be equal to C. Okay, now let us go to a converse of a theorem. Now you know what is a theorem. But the thing is, with a theorem, it must be proven. That statement is a mathematical conditional statement which must be proven. So a theorem must also be what will always be in the form P then Q. P then Q. But the Q part must always be what? In order for us to use the theorem, it must have been proven. It must have been proven. And remember again, I told you we can apply a theorem if and only if. So we can conclude if and only if the condition is met. So now let us go to the last one. The last part I'm going to discuss with you is a converse. It's a converse of a theorem. Converse of a theorem. Converse of a theorem. What is a converse of a theorem? A converse, by definition, I'm going to define this without actually writing it down. A converse of a theorem, we say, is a statement. A converse of a theorem is a statement that is formed by swapping. It is formed by swapping the condition and the conclusion of the original theorem. So if you go to the original theorem and swap the condition and the conclusion, that will become what? That will become a converse. Let us say, for instance, you are given that the original theorem states that if P, then Q. In this case, we can see that the condition is P and the conclusion is what? Is Q. So this becomes what? A theorem, is the original theorem. So if I want to get the converse of this will state that if, remember I said for converse, the condition and the conclusion must be swapped. It means they must be interchanged. Where there is P, I must have Q. Where there is Q, I must have what? P. So they will just be switched. So now where there is P, now I'm going to have what? Q as my condition for the converse. Then the conclusion will be what? Will be P. So what was the condition here will become what? A conclusion. What was the conclusion will become what? A condition on the converse. So converse is simply a statement that is formed by interchanging or swapping the condition and the conclusion of the original theorem. Some may consider this kind of lessons boring, and trust me, there's nothing boring here if you really want to know Euclidean geometry. If you want to claim yes, you can just jump straight into the theorems and then answer questions. But at the end of the day, you're going to have a problem with it. It's not going to work for you. So the only way you're going to survive here is by understanding fully the theorems. So now let us start with our theorems. Remember the theorem, the lesson, like I told you, it's all about theorems today. Before I introduce, oh yes, it's fine. One thing that I want you guys to understand about grade 11. In grade 11, there are a number of theorems. There are so many theorems. There are 9 excluding the converses. The moment if we introduce the converses, and then they become more than that. They become more than that. But that is not a problem. You know what I like about us is that we always find ways of making things more easier. But it's fine. So one thing that I like about grade 11 theorems is that they are grouped. They are grouped in 3 different categories. There are center theorems. Center theorems are theorems that involve the center of a circle. So they are only applicable when the center of a circle is given. And then there are also cyclic quadrilateral theorems, which are applicable once you see a cyclic quadrilateral. And then the last one are tangents theorems that are applicable the moment you see tangents in the diagram. So here I'm going to start with center theorems. Center theorems are theorems that involve the center of a circle. So they are applicable when you see center theorems. They are applicable once you see what the center of a circle. So it means if I give it a circle without the center, you can't even think about these theorems. So theorem number one that I'm going to discuss with you guys. Theorem number 1A states that if a line is drawn from the center of a circle, if a line is drawn from from, if a line, why am I having so many drawn? If a line is drawn, if a line is drawn from the center of a circle, perpendicular to a chord, then it bisects the chord. So this is the first theorem we're going to discuss. So this is the first theorem actually of grade 11 theorems, which is theorem 1a. If a line is drawn from the center of a circle, perpendicular to a chord, then it bisects the chord. If you look at this statement, you can see this is conditional statement. It consists of if and then. Remember I said conditional statement is a statement that consists of what? Of if and then. It's in the form if then, where if part always represent the condition, then part represent what? The conclusion. So the theorem is telling you of what the condition must be and of what the conclusion must be. So based on this theorem, what is the condition? The condition is a line that is drawn. Is a line that is drawn from the center of a circle perpendicular to a chord. And then the conclusion is it bisects the chord. Remember I told you that in order for a condition to be met, in order for us to have a conclusion, the condition must be met. So in order for this theorem to be applicable, we say a theorem is applicable if its condition is being met. So once I see the condition of a particular theorem, then I know that theorem is going to be applicable. And to apply a theorem, you conclude. When you conclude, then that is you applying a theorem. And remember I told you the only time you can be able to conclude is when the condition is being met. So there must be a condition. So once you see a condition, you know a conclusion must always must then follow. But with theorems educate you, or rather teach you of how to conclude for certain conditions. When you see this condition, this will always be a conclusion. So I'm calling this a theorem. It is a theorem, this one. It has been accepted to be true because it has been proven. But with us, we're also going to teach you how to prove theorems. But if I give you something as a theorem, it means it has been proven. It has been proven, and it can be proven to be true. So in this case, let us look at our theorem. Because Euclid is a topic of diagrams, it's about diagrams. Euclid is all about diagrams. You must be able to identify your condition on a diagram. You must understand how the condition of a particular theorem will appear. How is it going to appear on the diagram? When I'm looking at the diagram, what is it that I'm looking at in order for me to say, yes, the condition of this theorem has been met? So let us go to, I'm going to draw a diagram. So it means I'm going to need a circle, because this is all about what it talks. They're talking about a line that is drawn from the center of a circle. So it means I'm going to need what? A circle. So I'm going to draw a circle here, and then let me have this as my center. Yeah, and then let me draw my chord somewhere here. Say P2 is a chord. And then you draw a line from the center perpendicular to this chord. Something like this. Let me say this is M, and then this is O. Remember I said this is the center. So O in this case is the center. As you can see, OM is a chord. OM is a chord. So let us look at this. Is the condition of the theorem. So this is how it must appear actually. The condition of this theorem will always appear like this. Remember I said the condition is what? It's a line that is being drawn from the center perpendicular to a chord. Do you see a line that is being drawn here from the center perpendicular to a chord? Yes, I can see there is a line from the center here. You can see OM. Let me draw another chord somewhere here. Let me call this AB. And then draw something like this. Let me call this R. Exactly. So you can see in this case there are two lines that are being drawn from the center. There is OR. OR is drawn from the center to AB. The question is OR drawn perpendicular to AB? Is this the condition of this theorem? Guys, remember, you must be very careful. You must never make assumptions. If things are perpendicular to each other, it must be indicated. And the way to indicate that things are perpendicular is by using this symbol. This symbol here means what? The lines are perpendicular to each other. It means the angle formed between those two lines is 90 degrees. So this angle here, you can see the angle is being what? This symbol here explains that it shows you that two lines are perpendicular to each other. But when you come here, we can't say OR and AB are perpendicular to each other because I'm not having anything indicating that the two lines are perpendicular. So in this case, this is just a line drawn from the center to a chord. So I can't say anything about this line. But when I come here, yes, I can apply my theorem because I'm seeing what? The condition of this theorem. Remember, the condition of this theorem is applicable if I see a line that is being drawn from the center perpendicular to a chord. So is OM not a line drawn from the center? It is a line drawn from the center. But is OM drawn perpendicular to PQ? Yes, you can see they are forming what? An angle of 90 degrees here. So it means OM is a line from the center perpendicular to a chord. Therefore, the condition of this theorem is being met. And remember, I said if the condition is met, it means a conclusion. It means a conclusion is also what? Sorry, we can be able to we can apply the theorem. We can apply the theorem. And remember, I told you to apply a theorem, you simply what? Conclude for that particular theorem. So now, what is the conclusion of this theorem? They say then it bisects the chord. What is to bisect? To bisect means to divide, to cut, to split something into two equal parts. To divide, split, cut something into two equal parts. One thing that I want you guys to understand is that it is possible for a line to split another line. It is possible for a line to cut another line. It is possible. It is possible. If you give me something like this, let me say I've got a line like this here. And then you draw another, let me call this line PQ, for instance. And then you draw another line here. And let me just draw it here. That's fine here. Something like this. This line meet PQ at this point. And let me call this point Z is fine. Z is fine. So if you look at what we are having here. Whoa. Yeah. So if you look at what we are having here, you can see this line here, this line. It is cutting PQ at Z. The point where this line meet PQ is the point where this line is cutting what? PQ. So where does this line meet PQ? This line meet PQ at Z. So it means at Z, PQ will be cut into what? Into two portions, which is portion what? PZ and portion ZQ. So in this case, we say what? PQ has been cut off or been splitted by this line at Z into what? Into two portions. So there will be this portion here and this portion here. But, hello, in this case, I'm not going to say portion PZ and portion ZQ are equal. I'm not going to say, unless you tell me that this line is cutting or bisecting actually, unless if you tell me that this line bisect PQ. So it means this line, when this line cuts PQ, it will cut it in such a way that each part will be equal. Sorry, the portions are going to be equal to each other. Remember I said this line is cutting what? PQ into this portion and this portion. But if you say this line bisect PQ, it means it will cut it in such a way that this guy and this guy will be equal to one another. So in this case, we say what? PQ has been bisected. So in this case now, let us come here. Remember the theorem. Can I say OR here bisect AB? The theorem is telling us that in order for us to reach this conclusion, there must be a certain condition that has been met. I can't apply this conclusion if this condition is not met. The only time I can apply this conclusion is when this condition is being met. So it means I want to see a line that is being drawn from the center perpendicular to a chord. So in this case, do I see any line here? Here. Is OR drawn perpendicular to a chord? No. Yes, OR is drawn from the center, but is it perpendicular to a chord? No. So it means this line will simply split AB into two. into two portions, but we can't say these portions are going to be equal to each other because AB was not bisected here. But when we come here, OM is a line drawn from the center perpendicular to a chord. Is this not a condition of this theorem? It is. So if this is the condition of this theorem, therefore a conclusion must follow as a result. And what is the conclusion? When I've got a line drawn from the center perpendicular to a chord, I know that line must bisect the chord. So it means OM will bisect what? M2. It won't just split. It will split it in such a way that each portion will be equal to. It won't cut it. It won't just cut. It will cut in such a way that each portion, sorry, these portions here, these portions are going to be equal to each other. It means, in order for me to conclude here from this diagram, I can say therefore PM will be equal to MQ. Guys, remember, is OM not splitting MQ? It is into what? Into PM and MQ. And since OM is drawn perpendicular to PQ, it will split them in such a way that they will be equal to each other. So it means in this case, MP and MQ will be equal to each other. So this is the conclusion I'm going to reach for this diagram, for this condition actually. But here's the thing that I want you guys to understand. In Euclid, every time when you conclude, remember, the only time you can be able to reach a certain conclusion, that is if you have identified a condition, that is if a condition of a particular theorem has been met. So if the condition is being met, I can be able to conclude. Why am I reaching a certain conclusion? Because its condition was met. Because the condition was met. So if the condition is met, I can be able to conclude. So this is how we conclude. To conclude, imagine you exercise again. You exercise and lose weight. And then somebody comes and asks you, you've lost weight. How did you lose your weight? What are you going to say? Are you going to say, I lost weight because I lost weight? No, you're going to say, I lost weight. So to reason for a particular conclusion, you always use this condition. I lost weight because of what? You're going to say, I exercised. So if somebody says, how come you lost your weight? You simply say what? I exercise. So that becomes the reason. That becomes the reason for that particular conclusion. So when you conclude, you are being guided to reach a conclusion. You are being guided by the condition. The condition will always be the reason for you to reach a certain conclusion. Why am I saying MP is equal to MQ? I'm being guided by the condition. So in this case, so the reasoning is always, when you reason, you always use the condition. Why did you pass the test? I studied hard. You're not going to say I passed the test because I passed the you passed the test because you what? You studied you passed the test because you studied hard. So the reason for you to reach a certain conclusion is always, so it's always the condition. That condition becomes the reason why you reached a certain conclusion. So in this case, I'm going to say what? PM is equal to MQ. Reason being, because there is a line. There is a line drawn. Because of a line drawn from center perpendicular to a chord. So that was the reason why you said the chord will be bisected. Pella, you saying this and this are going to be equal to each other. You are just emphasizing that the chord will be bisected. Why was the chord bisected? The chord was bisected because of what? We had a line. We had a line drawn from the center perpendicular to a chord as a condition. So the condition is always your reason. When you give a reason for a particular conclusion, you just think about what was the condition here? What was the thing that was met here? What is that I managed to identify here? So when you reason, think about the condition. So let us go to the next question. The next theorem. The next theorem is theorem 1b. Theorem 1b. Theorem 1b. Theorem 1b. Theorem 1b. B. Theorem 1b states that if a line is drawn from the center of a circle to the midpoint of a chord, then it is perpendicular to the chord. Similarly, you can see the theorem consists of what? Of if and then. The theorem consists of if and then. Guys, here's the thing I want you to understand. With my theorems, they will be long as compared to what you will be given at your schools or maybe in some of the books. With me, it's because I want you guys to really understand. My lesson here, I'm concentrating more on the condition and the conclusion of the theorem. But if you go to some of the textbooks, they simplify the theorems. These theorems can be simplified as a line drawn from the center of a circle to the midpoint of a chord is perpendicular to the chord. The first one, when they simplify it, they say a line drawn from the center of a circle to the midpoint. So a line drawn from the center of a circle perpendicular to a chord bisects the chord. But with me, I'm not going to simplify the theorems. But I'm not saying there's anything wrong about simplifying. I can say yes, simplify the theorems. I can say yes, know those short theorems. Once you understand that theorem fully, you understand what is happening in that particular theorem, what is the condition and what is the conclusion. Because the easiest way to identify the condition and conclusion on a theorem is when it is in the form if then. So now let us continue. Let's continue. So let us look at this theorem. Remember, we know the if part represents what? The condition. The then part represents what? The conclusion. The then part, we know, is the conclusion. And the conclusion can only be, we can only get to conclude provided the condition was met. So based on this theorem, they are telling, guys, from the first theorem, they were telling you actually that every time when you come across a situation where a line is drawn from the center perpendicular to a chord, as a result, that line will bisect the chord. That's what they were telling you actually in that theorem. So in this theorem now, they are giving you another story. Here they are telling you that if a line is drawn from the center of a circle, to the midpoint of a chord, then it is perpendicular to the chord. So that's what they're telling you actually. That every time you come across a situation where there is a line that is being drawn from the center of the circle to the midpoint of a chord, then as a result, that line must be perpendicular to the chord. So the condition here is a line. It's a line that is being drawn from the center to the midpoint of a chord. Conclusion is that line must be perpendicular to the chord. The line must be perpendicular to the chord. Again, we need a diagram. We're going to need a diagram. O being the center somewhere here. Let me have my chord here. I'm going to give you two situations here. Ta-da. A, B, M. O is the center. Let me draw another chord here. P, Q, this being R. Then here they say AM and MB are equal. So now let us look at this theorem. How do I get to know that something is the midpoint of something? Because they are saying if a line is drawn from the center of a circle to the midpoint of a chord, then, so in this case we know the condition must be what? A line drawn from the center to the midpoint of a chord. So how do I know that a point is the midpoint of a chord? Can I say R is the midpoint of PQ? Guys, remember, in mathematics we don't assume. We don't make assumptions. We don't make assumptions. There must always be something guiding us. If I want something to be the midpoint, I will tell you that something is the midpoint. Unless, there are so many ways in which I can tell you. If I wanted R to be the midpoint, I could have told you, okay, R is the midpoint. Or I give you something to indicate that R is the midpoint. Remember, the midpoint is the middle point between 2 points. Is the middle point between 2 points. So the distance between the middle point to each point must be the same. The distance must be the same. So if I'm going to move, if we come here and look at this, I have indicated that AM and MB are equal. It means in this case, M will be the middle point. So I must indicate that a point is the middle point. Why am I saying this is the middle point? Because the distance we have from A to A and the distance I have from M to B are the same. Why am I saying they are the same? It's been indicated. Me doing this, I'm indicating that AM and MB are equal, which means M will be the midpoint of this chord. But here we can't say R is the midpoint. It is not indicated and it is not mentioned that R is the midpoint. Now, in which one can we be able to apply this? In which one is the theorem? So it is the condition of this theorem met. Can I apply it here? Am I having a line from the center? Yes. But is this line being drawn to the midpoint? Is R the midpoint of PQ? No, we can't say that. Nothing is being said about R. But now, when we come here, am I having a line from the center to the midpoint of a chord? Yes. Is M the midpoint of AB? Yes. Why am I saying M is the midpoint? It is indicated this guy and this guy are equal. Therefore, M becomes what? The midpoint. So in this case, I can apply the theorem, but here I cannot apply the theorem because the condition was not met here. But here the condition was met. Everything. The condition was met. So now, where do I apply the theorem? On this part, on the chord AB, but on chord PQ, I can't apply it. Now, let us conclude. When we conclude, that becomes a conclusion. Remember, they said, in this case, we said the condition is a line that is drawn from the center of the circle to the midpoint of the chord. If I see that as a condition, remember I said once a condition is met, then it must be followed by what? By a conclusion. Was the condition of this theorem met? Yes, it was met. I'm having a line from the center to the midpoint of a chord. Then can I conclude now can I continue to conclude now? Can I reach a conclusion? Can I apply my theorem? Yes, I can apply the theorem. Why? Because the condition was met. So what becomes a conclusion? Then it is perpendicular to the chord. What is perpendicular to the chord? That line which was drawn from the center to the midpoint must be perpendicular to the chord as a result. So it means I'm going to say what? OM is perpendicular to AB. Reason. Remember I told you when you reason, you use the condition. When you reason, you use the condition. The condition that was met becomes the reason for you to reach that particular conclusion. So you've reached a conclusion because of what? Because of the condition that was met. So what was the condition? The condition is a line. The condition here is a line. A line from center. Now let me erase this part of the circle. So the condition here, the condition becomes the reason for reaching a conclusion. So I'm going to say what? A line from center. Actually, you don't need to write a line. We simplify the condition. We don't write it in full. We simplify the condition. So I can just say what? Line from center. Line from center to the midpoint. To the midpoint of a chord. Then that becomes what? A reason. So that's how you're going to reason for this conclusion. So after you have proven that after you've concluded, this information now can be transferred to the diagram. You can go to the diagram and update it and show that this angle now will be what? 90. So that when you answer questions using your diagram, the information that you came up with is now on the diagram. Because everything that you write must also, everything that you come up with which was not part of the diagram, you must transfer it into the diagram. If you find something that was not there, you transfer it. Initially, I didn't know that this angle, if I didn't know the theorem, there is no way in which I could have known that this angle is going to be 90 degrees as a result. So it's the theorem that is guiding me. The theorem is telling me that if I come across this conclusion, then I must reach this conclusion. So if I come across this condition, I must reach this conclusion. I come across this, I reach this as a conclusion. So that's what the theorem is telling you. Let us go to the next one. So the next one, which is theorem number 2. It's also part of center theorems. So the first thing that you need to do before you write your theorems, you need to know the category where they fall. So these ones are center theorems. So even the next one that I'm going to write here. So this is kind of unique, unlike other theorems. I don't like this theorem for some reasons. I don't know. And it's the easiest though for learners to see or rather identify. Not to identify, to understand. Is the easiest theorem to understand, not to identify. But let me try my level best here to make you guys to so that you can be able to identify it on the diagram. So the theorem says that if a chord or an arc subtends angles at the center and the circumference of a circle, then the angle at the center is double the size of the angle at the circumference. So that's how the thingy we say the theorem at the circumference. Again, the theorem consists of what? If and then. If and then. So this theorem is long when you state it in full. It's very long. There are things about this theorem. Normally when people state this theorem, I don't know, but it's somehow. But yeah, they simplify it. They simply say the angle at the center is double the size of the angle at the circumference. That's how many people state the theorem. But with me here, like I said, the aim here is to give you guys full theorem so that I can be able to explain the condition and the conclusion in a proper manner. So now let us get to it. In this case, what are we having? Remember, we already know the if part represents what the condition. So in this case, we've got what? If a chord or an arc. So it means in this case, it's either you're dealing with what? With a chord or an arc. It doesn't matter. So it says that if a chord or an arc subtends angles at the center and the circumference of a circle, then as a result, the angle at the center is double the size of the angle at the circumference. That's what the theorem is saying to us. So it means in this case, the condition of this theorem is a chord or an arc in this case. The condition is a chord or an arc subtending angles at the center and at the circumference of a circle. So it means if I come across, in order for this theorem to be applicable, it's either a chord or an arc subtends an angle at the center and an angle at the circumference. So in simple terms, what they're trying to say to you here is a chord or an arc must subtend two angles, one being at the center and one being at the circumference. So there must be two angles. There must be two angles. Those angles must have been subtended either by what? By an arc. So by a chord or an arc. So let us start with a chord. Let me start with a chord. Let us look at a situation where the angles are being subtended by what? By a chord. For a chord, in order for this theorem to apply for a chord, there must be angles that are being subtended by the same chord. We don't need many chords, we need one chord subtending two angles, one being at the center and another one being at the circumference. But remember, those angles must have been subtended by the same chord. Let us look at this. So I'm going to give you a diagram here. So you guys will still remember we spoke about in part 1, we spoke about angle at the center, angle at the circumference. We also spoke about what angle subtended by the same, angle subtended by a chord and angle subtended by an arc. So we spoke about that. So now we're going to need that information here. That information is going to be needed here. So what I'm going to do here, I'm going to have my angle at the center. Remember we said an angle is at the center if its vertex is at the center and the arms are radii. We spoke about that. So you're gonna agree with me here. Let me just draw the diagram in such a way that the condition of that will be met. Here's my chord. May not be perfect. P, Q. Let me say this is angle O1. For another angle, for angle at the circumference, let me use this. May not be perfect. Yeah, something like that. So now let us look at this. Let me do this to fix this. Let's fix here. So this angle will be there. I'm going to have something like this. Yeah, something like this. There we go. There we go. So let me call this angle PQR. Angle R. Let us look at this diagram. Guys, like I said, we said this theorem is applicable if and only if there are two angles that are being subtended by the same chord. There are two angles that are being subtended by the same chord. One being at the center and another one being at the circumference. That's what they're simply telling you about that condition. If a chord subtends angles at the center and the circumference of the circle, then, so before we go there, what is the condition? The condition is what? It's a chord that is subtending angles, one at the center and another one at the circumference. So am I having here a chord that subtends an angle at the center? Am I having a chord that is also subtending an angle at the circumference? And am I having the same chord? So now let us look at this. You're going to agree with me that angle O1, if you understood what was discussed in part 1, you're going to agree with me that angle O1 is at the center. Because you can see the vertex of this angle is at the center. Remember we said the vertex for angle at the center, the vertex must be at the center. And the arms of the angle must be what? Radii. So is the vertex of angle O1 at the center? Yes. Are the arms of this angle, the arms is OP and OQ, are the arms of this angle radii? Yes. Is OP a radius? Yes. Is OQ a radius? Yes. Now I know angle O1 is at the center. So to identify this condition here, this is what you need to do. First of all, check if there is any angle at the center. In this case, yes, we've checked there is an angle at the center. After you have identified that angle which is at the center, check if that angle is being subtended by a chord or an arc. Is this angle subtended by a chord? Yes. Which chord subtends this angle is called PQ. Remember I told you that a chord can subtend an angle if the arms of that angle will touch the end point of that chord. Are the arms of this angle, which is OP and OQ, touching the end point of chord PQ? Yes. What are the end points of PQ? Is P and Q. This end point is touched by this arm, the other end point is touched by what? By OQ. So it means this angle is being subtended by chord what? PQ. So the procedure is identify the angle which is at the center. After you've identified it, check if it's being subtended by a chord or not. Is this angle subtended by a chord? Yes. Which chord subtends this angle is called PQ. Now you must check if this chord subtends any other angle at the circumference. Is this chord subtending any angle at the circumference? Yes. Which angle is that? Is R. Is R not at the circumference? It is at the circumference. Why am I saying this angle is at the circumference? The vertex of the angle is at the circumference. The vertex is at the circumference and the arms are chords. Is this arm not a chord? It is a chord. Is this not a chord? It is a chord. So now I know this angle is at the circumference. So now what I need to do, to confirm, is this angle subtended by chord PQ? Yes. Why am I saying this angle is being subtended by chord PQ? Because the arms are touching the end point of chord PQ, which is what? P and Q. This end point is touched by this arm, this one by this arm. So it means both angle O1 and angle R are being subtended by the same chord. But the question remains, are they being subtended at the center and the circumference? Yes. Is the condition of this theorem met? Yes. Remember, it is met if I see what? An angle at the center and angle at the circumference, however, being subtended by the same chord. Can I apply it here? Yes. Therefore, what becomes a conclusion? Let's continue. Then the angle at the center is double the size of the angle at the circumference. So it means the angle at the center is twice the angle at the circumference. If the angle at the circumference was x, this was going to be what? 2 times x, it was going to be what? 2x. So it always double. So the angle at the center will always be double the angle at the circumference. Whatever the angle at the circumference is, this one will be 2 times that. If this is 100, this will be 200. If this is 30, this will be 60. So this will always double the angle at the center. So to conclude here, we're going to say what? Therefore, angle O1 equal to 2 times angle at the circumference, which is angle what? R. Now there is something. Remember I said when you conclude, you must always give a reason. When you conclude, you must always give a reason. And I said to reason, you always use the condition. What I said to you was, I don't like this theorem for some reason. Because when you reason here for conclusion, you don't use what? The condition, you use the conclusion. And if I say to you, you must use the condition here, the problem is when they mark you, they will mark you wrong. Because they will want you to use the same reason that everybody's using. And the reason that everybody's using for this one is the angle at the center is double the size of the angle at the circumference. So when you reason here, this is one of the theorems where when you reason, you don't use the condition, you use what? You use the conclusion. And that is because of what? When this theorem is stated, stated in our books, the condition of the theorem is not indicated. It's not indicated. They only concentrate on what? On the conclusion, because there are so many things, of course, you can say from the conclusion. But yes, so here when we reason, in this theorem we don't use what? We don't use a conclusion. So we don't use a condition to reason, we use a conclusion. So here you're going to say what? Angle O1 is equal to 2 times angle R. Reason angle at center. Angle at center equal to 2 times angle at circumference. Angle at center equal to 2 times angle at the circumference. So that's how they reason for this one. That's how they reason. Now, there's one thing that I want you to understand. There's a mistake that I often see learners making based on this theorem. Remember we said it is applicable. Guys. A theorem is applicable when its condition is met. If the condition of a theorem is met, then a theorem is applicable. You can be able to conclude. And remember I said, when you conclude, you use what? You use the condition. It's only here where we don't use what? A condition. Because when the theorem, in many books, when it's being stated, when they state it, they only concentrate on the conclusion. Because usually there was this, when they state it, they say an angle at the center is double the size of the angle at the circumference. So of which that is a conclusion. But it's fine, it's fine, it's fine, it's fine. There's no need to attack people. Let us just continue. So now let us look at this another way, because you must be very careful. Remember the theorem says what? Said it is applicable. This theorem is applicable if a chord. I'm still on what? On chord. Let me concentrate on a chord again. The theorem is only applicable if a chord subtends two angles, one being at the center and one being at the circumference. There is one thing, even myself here, I did not include. Sometimes you just want to keep things short and it's already long. Imagine having to add. But there's something that I'm going to say to you. With a chord, you must be very careful. You must be very careful. Let us look at this. Let me say this is my chord. Tada. And let me draw it this way. Let me draw it this way. It will be easier to explain when it's like this. Tada, it's fine, it's fine. Let me say this is A, have B here. Then there is an angle here. Tada, tada. Remember I said the starting point of identifying this condition. If you want to identify the condition of this theorem, the first thing that you need to do is to check if there's any angle at the center. That is the starting point. So let me say this is O again, and then O1. And then you have let me say A, B, C. Let me say this is C. So I want us to look at angle O1. Is angle O1 at the center or not? Guys, it's fine. This is an angle. These are the arms. Just that they are not perfect. It's fine. Let us look at this. Now I want to identify. I want to check if the condition of this theorem is met here. So to do that, I must start off by identifying if there is an angle at the center. Do I see an angle at the center here? Yes. Is angle O1 at the center? Yes. Why am I saying angle O1 is at the center? Because the vertex of the angle is at the center and the arms of the angle are what? Radii. Now I've identified what? An angle at the center. So I'm now thinking about what? Let me go on. Maybe the condition of this theorem will be met here. Remember, it can only be met once I see an angle at the center. If I can't see an angle at the center, I must just forget about it. There's no need to continue thinking about it. So first of all, I must be able to identify an angle at the center, of which in this case, I have identified my angle at the center, which is angle what? O1. So angle O1 is an angle at the center. I said after identifying your angle, remember you're also going to need what? Another angle that is being subtended by this. Sorry, that is being subtended at the circumference. But now, before you do that, you must check if that angle at the center is being subtended by an arc or a chord. Is angle O1 subtended by an arc or a chord? Is being subtended by a chord. Which chord subtended angle O1 is AB. You can see this angle is being enclosed by this chord. You can see the arms of this angle are touching A and B. It means this angle is subtended by chord AB. But the question is chord AB subtending any angle at the circumference? Yes, chord AB is subtending what? Angle C at the circumference. You can see C is an angle at the circumference. Why am I saying angle C is at the circumference? Because the vertex is at the circumference. And the arms are what? Chords. This arm is a chord, this arm is a chord. Therefore, this angle is at the circumference. But is this angle subtended by the same chord which subtends the angle at the center? Yes. Now, can we say the condition is being met? One can say yes, and trust me, you won't be wrong based on what I gave you. But one thing that I want you to know is, when we talk about angles being subtended by the same chord at the center and the circumference, those angles must be subtended on the same side of the chord. Because if you can look at this angle is above the chord, this one is below the chord. In this case, it won't work. The angles must have been subtended by the same chord on the same side of the chord. If you can look at this, I don't know if this is clear. Yeah, so, yeah, if you look at this, let me say this angle is Z. If you look at angle Z, you can see that angle Z is being subtended by the same chord which subtends the angle at the center. The angle at the center is subtended by chord AB. And the same chord AB also subtend what? Angle Z. So in this case, angle Z and angle O1 are being subtended by the same chord at the same side of the chord. They are both above the chord. So in this case, you can say angle O1 is 2 times angle Z. Then you give that reason. Angle at center, 2 times angle at the circumference. But when you come to this angle, yes, this angle is subtended by the same chord which subtends the angle at the center. But in this case, the two are not being subtended on the same side of the chord. So you can't say angle O1 is twice angle C here. It's not going to work. So in this case, angle O1 is not equal to angle 2 times. It's not equal to 2 times angle C, because these two are not being subtended on the same side of the chord. But if I come and give you something again like this, it doesn't matter. If I come and give you something like this, let me say tada, you can see this angle is also subtended by the same chord. But is this angle subtended on the same side with the angle at the center? Yes, they are both above. Therefore, angle O1, or let me say this is now T. So you can see now, in this case, angle O1 will be twice what? Angle T. Same reason. Angle at center, twice angle at the circumference. But what you need to be careful about is those angles must have been subtended on the same side of the chord. So let us go to an arc. Let us go to an arc. Still the same theorem, but for an arc now. For an arc. Now let us go to an arc. Again, it's either we've got a chord subtending two angles, one at the center and one at the circumference, or we have an arc subtending what? Angles, one at the center, one at the circumference. And there is one thing that I want you to understand. Once the angle is at the center or the circumference, that angle is always subtended. You will never have an angle at the center or a chord. Sorry, you'll never have an angle that is at the center or the circumference and you find that that angle is not being subtended. No way. An angle will never be at the center and not be subtended. An angle will never be at the circumference and not be subtended. So once you see the angle at the center, you already know that angle is being subtended. Once you see an angle at the circumference, you already know that angle is being subtended. I told you last time, if you look at this angle here, tada, if you look at this angle here, tada, angle Z, let me say Z, let me say this is A, this is B. You can see in this case, Z is an angle where at the circumference. Why am I saying Z is at the circumference? The vertex is what? Is at the circumference and the arms are chords. So if you can look at this angle, you can see this angle is being subtended by an arc. So the angle is subtended by an arc, unless if I introduce a chord joining these 2 points. Therefore, I will say the angle is being subtended by what? By a chord. So what I'm trying to say to you is there is no way that you can find an angle at the center that is not being subtended. There is no way. So once the angle is at the center, it will always be subtended, but either by what? A chord or an arc. So similarly, if you give me something like this, you look at this angle. Let me say tada. You say tada. And then O is the center. Then I've got angle O1. So this is angle O1. Let me say this is P, this is Q. If you look at this angle here, angle O1 is at the center. Why am I saying angle O1 is at the center? The vertex is at the center and the arms are what? Are radii. So with this situation, we know that therefore the angle is being subtended. It will never be at the center and not be subtended. It's either it's being subtended by an arc. It's either the arc is the one that is enclosing the angle, or there will be a chord that is enclosing the angle. So it will be one of the two every time. So I can't have an angle at the center and that angle is not being subtended. I can't have an angle at the circumference and that angle is not subtended. So every time when you see an angle at the center, you must know that angle is being subtended. When you see an angle at the circumference, you must know that angle is subtended. So what I'm going to do now, I'm going to give an example for an arc. Tada. So in this case, I'm still going to have what? O as my center. So there's angle O1 here. And then let me say this is A, and then this is B. And then let me have another arc, so another angle here. And let me have it like this, yeah. Ta-da. Now let us look at this. So let me call this angle ABC. Angle C. So now let us look at this now. Remember I said this theorem, the starting point, if you want to know whether the condition of this theorem exists, you must start off by checking if there is an angle at the center. So do you see any angle at the center here? If I see the angle at the center, I must think about this theorem. I'm not saying that will be enough. I must therefore confirm if that angle is being subtended by the same by an arc or a chord, and is that chord or arc subtending any other angle at the circumference? We spoke about it. So now let me look at this. Let us look at this. Is angle O1 at the center or not? Am I having an angle at the center here? Yes. Which angle is that? Angle O1. We know why this angle is at the center, because the vertex is at the center and the arms are what? Are radii. The arms are radii. Now let us look at the angle. Remember, I said once the angle is at the center, that angle, without any doubt, that angle is either being subtended by an arc or a chord. So now, is angle O1 at the center? Yes. So it means, therefore, this angle is being subtended. I just need to find out what is subtending this angle. Is it a chord or an arc? If you look at this angle is being subtended by an arc. It's subtended by an arc. Which arc? Arc AB. Arc AB subtend angle O1. Then I need to check if this arc subtend any other angle at the circumference. Do you see any angle at the circumference with its arms touching the end point of this chord? Remember I said if an arc is to subtend an angle, the arms of that angle must touch the end point of the chord, of the arc. So you can see that angle C is an angle at the circumference. The arms of this angle are what? C, B, and what? A, B. If you look at the arms of this angle, are they touching A and B? Yes. So it means this angle is also subtended by what? By this arc. So it means arc AB is subtending two angles, one at the center and one at the circumference. Can I be able to conclude here? Yes. What becomes the conclusion? Then the angle at the center, angle O1, will be equal to 2 times angle C. Why? Same reason. Angle at center, 2 times angle at the circumference. You remember that reason? So in this case here, these two angles, the condition of this theorem is being met, because there are two angles, one at the center and one at the circumference, and being subtended by the same arc. Therefore, the theorem here will be what? Will be met. So let us continue. So I'm going to stop here for today for angle at the center. There are so many things that I'm still going to talk about, guys, under the angle at the center. Actually, under every theorem that I'm discussing with you. So the next theorem becomes what? Angle at the what do you call it? Angle, or the next theorem becomes what? Theorem number 3. Yeah, theorem number 3. Let me erase. It was like, yeah. So the next theorem, which is theorem number 3. Theorem 3. So it will be theorem 3A, because it also has a converse. So states that if a diameter subtends an angle, if a diameter subtend an angle at the something's not. If a diameter subtend an angle at the circumference of a circle, then the angle is a right angle. Then the angle is right angle. So that is our theorem, theorem 3A. That is our theorem, theorem 3A. It says that if a diameter subtend an angle at the circumference of a circle, then the angle is a right angle. So what is the condition here? The condition in this case, like I said, the if part and then the then part. So the condition here is a diameter that subtends an angle as the circumference of a circle. So it means for this theorem to be applicable, I must see an angle that is being subtended by a diameter at the circumference. So if I don't see a diameter subtending any angle at the circumference, I can't even think about this theorem. I can only think about this theorem once I see what? I see a diameter subtending any angle. It doesn't matter where the angle is. As long as I see a diameter subtending an angle at the circumference, then I can think about this theorem. So that is the only time where this theorem will be applicable. So now I'm going to give you guys a diagram. So when we apply, we're just going to conclude. Then the angle is a right angle. So I'm going to draw a diagram having the condition of this theorem being met. We know what is a diameter. We said a diameter is a chord. A diameter is a chord that passes through the center of a circle. So it means a diameter can also subtend an angle. If it's a chord, it can also subtend an angle. Remember, if a chord subtends an angle and the diameter is a chord, it means a chord can also subtend an angle. There's nothing that a chord can do that a diameter cannot do. But there are so many things that a diameter can do that not all chords can do. It's fine. Just like more. Now, let us look at this. So I'm having what? AB here, which is a diameter. So AB is a chord, you can see. Remember, a chord is a line that joins 2 points along the circumference. You can see this line is joining A and B along the circumference. So it's a chord. But because it passes through the center, this is the center, guys. This is the center. Then AB in this case becomes what? AB becomes a diameter. So remember, the theorem says what? In order for this theorem to be applicable, we said in order for a theorem to be applicable, its condition must be met. So the condition of this theorem is met if there is what? A diameter that is subtending an angle at the circumference. So in this case, I've got a diameter. So let us say this diameter subtend an angle somewhere here. Ta-da. So let me call this what? C. So now, by looking at this, you can see that angle C is an angle. Angle C is an angle at the circumference. Why? You know the reason, the vertex and the arms. You can see that. Now, the question is C being subtended by AB? Yes. Why am I saying C is subtended by AB? The arms of C are touching the endpoints of what? Of AB. Is AB not a diameter? It is a diameter. So am I having a diameter that is subtending an angle at the circumference? Yes. Can I say the condition of this theorem is met? Yes. Remember, we said the condition here is a diameter that subtends an angle at the circumference. Am I having a diameter that is subtending an angle at the circumference? Yes. Now can I conclude? Yes. What becomes the conclusion? Then the angle is a right angle. So it means that angle that has been subtended by that diameter will be what? A right angle. Which angle is being subtended by this diameter is angle C. It means this angle here will be a right angle. What is a right angle? A right angle is a 90-degree angle. A right angle is a 90-degree angle. So it means the size of this angle here, angle C actually, angle C will be equal to 90 degrees. So that's what the conclusion is going to be. Why am I saying angle AC? Remember I said when you reason, you use the conclusion. You use the condition. So in this case, you're going to say what? Angle C is equal to 90 degrees. And let me write it here, I'll reason this side. So I'm going to say what? Angle C, therefore, is equal to 90 degrees. What is the reason? So my reason will be what? Angle subtended by a diameter. Angle subtended by a diameter. Angle subtended by a diameter. So that's how we reason here, which is the condition. I'm saying this angle is equal to 90 degrees because this angle has been subtended by a diameter. Remember the condition says that if a diameter subtend an angle at the circumference, then the angle must be 90 degrees. Is this angle not the angle subtended by a diameter? It is. That is what we are saying. The reason is what? The condition. This is the condition actually. Angle subtended by a diameter. So we are done. We are done. So now the last one, which is the converse of the theorem. Okay, guys, I'm going to stop here. So you can go to the diagram and update the diagram. If you find something that was not in the diagram, if you prove something and it was not in the diagram, you can go transfer the information in the diagram to keep your diagram updated. So after proving this, you can come and say, therefore, this angle here will be what? 90 degrees. This and that will be perpendicular to each other. So that will help you when you proceed with other questions. The diagram that is updated every time is always useful and helpful. So let us go to the last one, which is the converse of this theorem. Let us go to the converse of this theorem. So the converse says that if a diameter sorry, not a diameter. God. If a chord subtends a right angle, if a chord subtend a right angle, if a chord subtend a right angle at the circumference of a circle, then the chord is a diameter. Then the chord is a diameter. If a chord subtend a right angle at the circumference of a circle, then the chord is a diameter. So in this case, what is the condition? In this case, the condition is a chord that subtend a right angle at the circumference. So it means in this case, what must exist is there must be a chord that is subtending a right angle at the circumference. Do we know what is a right angle? Yes, it's a 90-degree angle. So if I see a chord subtending an angle at the circumference that is equal to 90 degrees, then I can apply the theorem. I can say the condition of the theorem has been met. So I'm just going to give you guys a simple chord. Guys, remember, we never make assumptions. So PQ is not a diameter, it's a chord, because it is not going, there is no center indicated on that line. So it's not going, unless if I tell you that it's a chord. So it's a diameter, then yes. But in this case, PQ is just what? It's just a chord. It's just a chord. It's not passing through the center. Then now they say if a chord subtend a right angle at the circumference, let me say this angle is 90 degrees, and then call it PQR. Let me call it R. So if you look at this, is the condition of this theorem met? Yes, it is being met. Remember, we said the condition of this theorem will be met if a chord subtend a right angle at the circumference of a circle. So do I see this chord subtending any angle at the circumference? Yes. Which angle is being subtended by this chord at the circumference? It's angle R. And what is the size of the angle? It's 90 degrees. It's 90 degrees, not a right angle. It's a right angle. So you're going to agree with me that chord PQ subtends a right angle at the circumference. So it means the condition of this theorem has been what? Met. Now, can I conclude? Yes, I can conclude. How do we conclude? Then the chord is a diameter. So it means PQ here. PQ will be a diameter. Then PQ is a diameter. Reason. So with this one to reason, we use the condition of the original theorem. Remember, this is a so this is condition. This is 3b. This is 3b. So when we reason for converses, because this is a converse statement. So when we reason for converses, we use what? We use the condition of the original theorem. But I will come and have a thingy. I'm going to create a lesson where we'll be talking strictly about what reasons, more especially where you're gonna have to use the converse of the theorem and stuff. For now I'm very tired. I don't think I can be able to emphasize on this one. So, but the reason for this one for now, you just need to say what? Converse angle subtended by a diameter. There are still other reasons we use for these things, but we'll talk about that. For now, guys, I'm tired, to be quite honest. I never thought I was going to last until this point, but at least I managed. Guys, thank you for watching part 2. And I'm just hoping you guys will understand, and just understand everything that I discussed here. It doesn't matter what I didn't discuss, but with what I discussed here, please make sure you understand everything. Then I'm going to explain everything, guys, there is to know about your Euclid. It's going to happen with all the topics. I'm not going to leave anything unattended. So, and guys, just to emphasize on one thing, my lessons are not for learners who want to cram mathematics. I'm creating this lesson so that you get to understand your maths better. So if your aim is to cram mathematics, trust me, these lessons are not going to work for you. They are not going to work for you. And again, I'm going to tell you, there is no way you're going to make it in mathematics if you want to go that way. You want to cram mathematics. You want those, shortcuts, and those things are not going to work. The quick fixes are not going to work. So, guys, again, thank you for watching part 2, and I hope I will see you guys in part 3. Hope you watch part 3 as well. And guys, please don't forget to subscribe and to tell your friends about these lessons. Tell your friends. The aim is to reach as many learners as possible. If I can help as many as possible, that is the goal. Actually, at the end of the day, that is my goal. And thank you again. Until part 3. Ta-da.